Okay, so this is our case study for the end of discrete random variables. And as I said on Piazza, we're going to look at something different. What we're going to do is we're going to look at modelling knife homicides in the UK. So, first of all, let's go and have a look. This is, I had a search around, and eventually I found that this is probably our best data set. So this is the House of Commons for the UK Library. They did a report on knife crime statistics. And there was a nice Excel spreadsheet here. So I went and downloaded that. And let's have a look at what we've got. So we've got numerous tabs in here, but I thought this was probably the nicest one to look at. What we've got here is each row is a year, going back to about 1977, and we've got the number of deaths by sharp instrument, blunt instrument, etc. And we've got our totals. So this is the data we're going to analyse. So you've been so good so far this semester. We're going to do what Jono loves to do. We're going to do some analysis and data science in R. So let's open it up. So welcome to R and R Studio. Now, I'm not expecting you to learn R, but if you're going to do data science, this is probably the best thing to learn. So let me just break this down. Over here, you've got your console. Down here, you've got your files. Here is a bit about environments and stuff like that. And what I'm doing here is I've actually made what we call an R markdown script. And I'll show you why I do that at the end. Basically, this can have code in here, but what I've got here is I've got a title. I've got my who I am, obviously, which lecture it is, and we can call this was lecture, I think this is lecture 12, semester 1. I got some stuff ready to go, some setup. So what we're going to do first of all is you can see every so often I have these chunks and I can put R commands in here. So I'm going to need some extra add-on packages to do this. To do this, we're going to use the pacman, which is a package manager. : tells me that inside that there's a function called pload, and this is going to load tidyverse, read Excel, and janitor. So we're going to run that. And over the console, you can see it got run. And now I'm going to read in my knife data. Well, can't find it, so I'll just go and set my working directory. And rerun that. And then let's have a look. So what have we done here? We've got a command that says read Excel. I said where the data is. I said which sheet I want, which is the TA2. As you can see here, the TA2. And the other thing I noticed is the first 2 rows of this is just a little bit of header information. Row 1 and row 2 I don't want. So I basically said skip them. So we've got this first column, which is cool because it didn't have a name in the spreadsheet, just ... 1. We've got sharp instrument, blunt instrument, etc. So each row is a year. We've altogether got these 10 plus another 32, so we've got 42, and we've got all these variables. So before I do anything, I'm going to have to do some cleaning. So let's have a look at what I've done here. So if you've not seen it before, this little %, means then. It's called a migrate R. So this says take our data frame. So this spreadsheet here, it's called a data frame. Take it. Then I'm going to use janitor to clean the names, just make them nice, user friendly. Then I'm going to rename the first one, which will after that be called X1 as year. Then the next thing I'm going to do is you'll find that some of these, when I clean them, will say things like motor vehicle 7. So this is just a quick way of saying remove numbers from any column names. We don't need the total, and then we'll have a look at what we've done. So if I run that, what we can see now is I've got a column year, it says sharp instrument, blunt instrument, hitting, kicking, strangulation, etc. So that's all good. The next thing I've got is I've got a bit of a problem with this data. Let me have a better look. So if we go to environment and click on knife attacks clean, you can see here it says 1977, 1978, that's all good. And then suddenly it's got this extra, it's going 97, 98. So I'm going to do this one. I'm going to recode this as 1998. This one's 1999, etc. So I've got a quick hack. I'm basically removing the digits in between. And the problem is you'll find that there's one year that ends up being 19,000. I've converted to 2,000. So run that. The other thing I've done is I said make it into, if you look here, it says it's a character. I want it to be a number. So if we just do knife attacks clean and run that, there you are. Now it says it's a DBL, which is a double, so it's a number. And we've got all these numbers ready to go. So we clean our data. As I said, that's a little bit advanced for you. Well, some of you might be very experienced, that's all fine. But let's now look at some visualization. So what I'm going to do is I'm going to use ggplot2. So I'm going to take my data. I'm going to make it into a long form. What do I mean by that? Well, let me show you. If I do this, what you see now is instead of having a row for each year, it has a row for each observation. So it says the first observation is in year 1977. It was a sharp instrument and it was 135 deaths. 1977 blunt instrument. So it's converting to what we call the long form. Then I'm going to do a plot. And this plot, the x-axis is going to be year. The y value is going to be our value, which is the number of deaths. And we're going to make it coloured by whether it's sharp instrument, blunt instrument. We're going to add some points, we're going to add some lines, and then we're going to wrap it. So let's have a look at this. Give it a second. And let's zoom in. So what have we got here? We've got on the x-axis the year. On the y-axis we've got the number of deaths, and all these are for blunt instruments. So we can see with blunt instruments, we generally see it cascades off. Burning, there was a huge increase of burning. There was 80 deaths of burning in 1980. I haven't investigated what that was about. Explosion, again, we have a huge one here. Unfortunately, I think that is going to be the terrorist attack in London. If you remember that, there was a bus that was blown up in London. But what we're interested in, if we go all the way down, we're interested in this sharp instruments. Because what we see is there's generally an increase, then it seems to decrease, but there's a real peak at 280 here. So let's think about what we've got here. We have the number of events per year. Now there's different ways that we could model this, but the one that we were introduced to in our course was the Poisson distribution. So what I'd like to do is work out how to choose an appropriate Poisson distribution. So what I'm going to do is I'm going to show you how I'd actually do it. We're going to do a thing called likelihood theory. You'll do this in second semester in stats modeling and inference, but we'll look at it here. We'll see how this works. So let's set up some notation. First of all, we're going to let yi be the random variable that represents the number of deaths by sharp instruments in year I. So, and we'll call the first year, year one, etc. counted that way. So what I want is and we'll come back to this again when we get to bivariate distributions, I want a joint distribution. So instead of me just going, let's model year one, let's model all the years. So what I want a distribution that will tell me the probability that year one has y1 deaths, and I'm going to use the comma to represent and, y2 is y2, all the way up to yn equals yn. So we've got, altogether, n random variables. And I want the distribution of all of them. I want the intersection of all of them. Well, we're going to assume that each of these random variables are independent. So I can write this as the probability that y1 equals y1 times by the probability that y2 equals y2, all the way up to the probability that yn equals yn. And why? Because we're assuming they're independent. Well, probability y1 equals y1, well, that is a Poisson distribution. You know what that is. So we can actually write this as the product as I goes from 1 to n. We're going to have e to the minus lambda, lambda to the yi over yi factorial. In fact, we could simplify that. If you think about this product, this is e to the minus n lambda, lambda to the summation as I goes from 1 to n yi over the product as I goes from 1 to n yi factorial. Now, if you think about it, I could use this probability mass function. I could go, I think lambda equals 100, and then I can say, what's the probability the first year we have 10, the second year we have 3, and you can substitute that in and get your probability. But here's the key idea in likelihood. This function I have at the moment, this thing here, relates our parameter to the observations. And normally the way we'd use it is I would give you, in most of your assignments, a parameter and say, calculate a probability. But we can use the same thing and say, what if I've actually observed the yi's? What if I put the yi's in? I could now try putting in different values of lambda and see how likely it is. So it's called a likelihood. Or what we can do here is we can say, let's try different values of lambda and find the one that maximizes this the most. So we're going to substitute in our observed values, and then we're substituting our observed values, and we're going to take this and we're going to find which value of lambda will maximize it. Well, how do you maximize it? Basically, we're going to use calculus. And we're going to make it a bit easier for ourselves. Because if I want to find the maximum of a function, as long as that function is sufficiently nice, I could instead maximize the log of that function. So what I'm going to do is I'm going to take logs. So we will take logs. When we do that, we call it the log likelihood. So if I take logs, I now get minus n lambda plus the summation as I goes from 1 to n yi log lambda minus the log of the product I goes from 1 to n yi factorial. And if ever I want to find the maximum minimum of a function, what you do is you differentiate it with respect to the thing you're trying to optimize over, and you set it equal to 0. So let's do d by d lambda. That's going to equal minus n plus the summation as I goes from 1 to n yi over lambda. This final term is great. This has no lambda in it. This is complicated, but it's a complicated constant. We'll just get rid of it. So now I've got my function. I'm going to set that equal to 0. So I've got minus n plus the summation as I goes from 1 to n yi over lambda equals 0. And if we rearrange that, and I'll let you do that yourself, you should get that lambda equals the summation as I goes from 1 to n yi over n. And because we're estimating this lambda, we don't know the true lambda. We're saying, with this data we've got, what value would have maximized it? We will indicate that by putting a little hat over it, which tells me that's an estimate of a parameter. And hopefully you recognize this. This is just the sample mean. So that's really nice. If I have a load of observations that I believe, in this case, each year is from a Poisson distribution with the same rate lambda, I can just average the number of events, and that will give me an estimate of my lambda. So, given that, let's go back to our code. So let's switch this down. So let's fit it. What I'm going to do is I'm going to fit a Poisson distribution to all the years up to 2017. And then I'm going to predict, using that, predict what 2018, or see if 2018 is extreme. So we take our knife attacks. I'm going to filter for all the years that are less than or equal to 2017. And then I'm going to get a summary. I'm going to get the value m, which is going to be the mean of the number of events. So if we do that, so that's 208. So lambda hat is 208. So I've set that. So we believe that the best distribution to fit this data would be a Poisson distribution with a lambda of 208. Okay, so let's see how many we got in 2018. So in 2018, we got 285. So is that extreme or not? Well, we could ask the simple question of, what's the probability that y is greater than or equal to 285, that is, I get the same number of deaths as that or more extreme, given we know that lambda equals 208. So that could be 1 minus the probability that y is less than or equal to 284, which is 1 minus, p plus 284 with a lambda of 208. So let's do that in R. 2.43 times 10 to the minus 7. That is really extreme. To visualize how extreme that is, what I'm going to do is I'm going to look at I'm going to basically produce my probability mass function and have a look at it. So let's run this. So here is your probability mass function. Each of these is the height of the probability of that value being the one we've given. Here's the value we observe. This is all the likely values. This is way out. It's definitely, if you use the data pre-2018, 2018 is really extreme compared. Now, we assume that a Poisson is good to go. But there's a couple of ways we could check that. First of all, let's run this code. This gives me now in first year, if you've done SAM or Stat Part 1 or other stats courses, you will have seen what we call a normal quantile plot, which is a way of testing if data is normally distributed. Well, you can do the same with other distributions. On the X, I've got the theoretical quantiles for Poisson. Here's my sample. And ideally what you'd see is if the data is distributed with a Poisson distribution, this should roughly lie on this. You see there's a fair bit of deviation away up in this area. The other thing we can do as a quick check is we know that the mean and the variance of a Poisson distribution are both lambda. So if I've got data that's from a Poisson distribution, we should see that the mean and the variance are about the same. So what I'm going to do is I'm going to calculate the mean for our data and the variance of our data and compare them. And what we have here is our mean is 208, but our variance is 1084. So the Poisson's not a bad start, but it's not good enough. This data is what we call over-dispersed, and you'd need something a bit better than a Poisson, something that can deal with that extra what we call heteroskedasticity. So there you are. A very simple example of taking a distribution you've learned and applying it to real data and ask a simple question of, do we have a major increase in knife attacks? So that's everything for now. Next time we will start continuous random variables. Thank you very much.